Okay, can everyone hear me okay? Great. So, how are people going with the course? Are you feeling reasonably comfortable with the material, or are there things you're struggling with? Ha! Yeah. And also there's functions which exist in PHP, but they behave completely differently to the C version. So that might do your head in a little bit. Like the string functions, while they have the same name, behave completely different, and they have a different performance. Well, when you think about it this way, C has been around. Yep. C has been around as a language since 1971. And we're now in 2016, coming into 2017. So that's, a good 45 or so, 45? Yeah, 45 years that it's been around, and it's not showing any signs of disappearing. If you have a look, for example, at any of the online materials around operating systems programming, it's all still in C. Alrighty, so what we're going to do today is finish off some of the general stuff around yeah, so what we're going to do is finish off some of the general stuff around making basic C programs. And so we'll have a look at modules and that kind of stuff. So, and we're also going to have a look at time and random and things like that in C. So, obviously the purpose for us to write a C program is in fact to actually solve a problem. In fact, to usefully solve a problem. So with that in mind, that's a prominent focus of what we're doing. I try to make the examples we're going to do actually be practical. But we've only got limited time. We can't write massive, huge systems in the times we've got, but we can get going in that direction. Okay. So, there are a range of concepts which can come in handy when you're developing a solution to a problem, and often the temptation is to skip over those concepts, which we very much discourage, because they're actually going to be key to your they form a good grounding. So one of those things is the importance of planning and design. So we put a lot of emphasis in this course on you actually planning the structure of your program. For example, It's a pretty common thing for me to do when I've actually got an idea for a program, is in fact to draw out what the data structures might look like first, and then build my program around those data structure design. So for example, if you have a look at assignment 1, each module does a certain thing. Like for example, we have the game rules, which is the rules by which the game is played. So for example, things like how is a winner decided and things like that. Then we've got a game board module. So they're all the things which have to do with the game board itself and manipulating of the game board and so on. Game, then there's a scoreboard. So each one is, in a sense, its own unit. Yeah. And that's a fairly important part of designing software, is that each module, so each C and H pair, describe essentially what in a language like Java would be an object. So we the only difference really in the way we would program, say, in C is in fact that our objects, we have to explicitly pass them into functions. So that's the main one of the main differences. Okay. So a key idea that you're going to find handy is the idea of stepwise refinement, top-down design, and that is really that we break tasks into smaller tasks. So really our process of design, we break things down into smaller and smaller units, and generally speaking, I reckon that units which are above, say, which are longer than 1 or 2 screens are too big for us to actually manage. So try to actually make the units, the functions, 1 or 2 screens or no larger than that. Okay? Okay. 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 We might come back to this if we've got time, actually. So this is probably an example that you might want to come back to and have a look at, and if we have some time, we might actually do it. Yeah. But looking at this, right? Say you got a game where you've got rooms, and in each room you've got items, and there might be players and that kind of thing. So the thing is, what would make a good object? So we start by thinking of the nouns or the things. So yeah, a board is a good candidate, and as Richard mentioned and others have mentioned, probably a two-dimensional array. Would be a good potential structure. And we might manage what each characters are doing in each room. So what would moving between rooms mean, do you think? If I as a character move between rooms, how is that going to be represented? Correct. You would need some kind of coordinates. Yeah. So the question is whether I actually represent that in the matrix, or do I represent in the board, or do I represent that in the character? And both are kind of reasonable depending on what else is going on. If we have many different characters who might be in a particular room, maybe putting it into the character, what their location is. Yeah. Okay. So there are options, right? And we're not really going to assess you on your software design or whatever. I guess the point is that stuff that you learnt in, like you may have learnt if you've done a unit like Software Engineering Fundamentals, all that stuff applies here. Just because it's a procedural language does not mean that all of a sudden we've given up on certain concepts or whatever. It all applies. And there are important ambiguities in any description. So, for example, if we have a look back here, you've been asked to... The game board is made up of rooms. In each room there may be one or more characters. Each character may hold multiple items. So we've got the idea of player characters and non-player characters. But every description is going to have some ambiguities that we need to take note of and solve or whatever. And let's talk about modules as well. A module is let's double check something. Oh, I think I've got the wrong copy. Hang on. Hang on. Yeah. So a module is a C and H pair that describe an object and its behaviors. Something I've realised, I think I'm using an old version of the slide, so just give me a second, I'll just open up the newer one. Okay. Yeah. Okay. Okay, this is looking better. Okay. Let's keep moving. So, two ideas which are really important when you're designing a module are coherence and coupling. That is, each module needs to be self-contained, and there shouldn't be unnecessary links between components. Like, for example, if you look at your assignment, the player module shouldn't know too much about the internal workings of game rules. It might need to call some functions in there, but it's like a black box, it's a closed unit. We don't actually know too much about the details inside, and so there isn't excessive coupling. That's a pretty important concept. So these concepts of coherence and coupling will come up often in software development. Okay, so function abstraction. This is where it's this very idea that we don't need to know the internals. We just need to know the things that a module can do for us. And so that's key. So if a function only performs a few minor tasks, we can test it in isolation, and in that way we can ensure that when a bug arises, we know where it occurs. So the understanding of the structure of a program is key. It's really important. And we can also, as well as that kind of idea of functional abstraction, we can also talk about data abstraction. That is, you already do it, right? You already talk about a 2D array. And you know, when we talk about that, everyone knows what we're talking about. But it's an abstraction. In fact, the details of how that's implemented can be reasonably complex. But we have this idea of we've got something called an array, and we can even go higher level than that and talk about a collection, right? And talk about an array as a kind of collection. And there's different kinds of collections, right? We can have also a list, which is a kind of collection. A tree is a kind of collection. And there are things we might want to do on each collection, regardless of what the kind of collection is. And so all collections involve grouping related pieces of information together. Or in every data structure, we group related pieces of information together. We understand or specify what meaningful operations could be done on that collection. And we might enforce certain restrictions on the use of that collection. For example, we might decide there are certain operations that functions outside the collection shouldn't know about. Every language has a way for us to do some kind of information hiding. C has its own way of doing it. It's not as, well, you might say it's not as robust as what you might have come across in languages like, say, Java or Python or whatever, but it's there. Other things we do is we separate out the implementation. And so that's in essence part of the role of your header file versus your C file. Other modules that use services from this module don't need to know how it's implemented internally. They just need to know enough stuff to be able to use it. And so in essence we can change that internal representation. For example, if the internal representation of our board, not sure why we would do this, or we might, we change it from a 1D array, so we change it from a 2D array to a 1D array, where we actually handle jumping along in memory and things like this and so on ourselves rather than letting the compiler do it. We could do that. So the thing is that there's this thing called a game board, and everywhere else should just use that game board. It doesn't need to know the internals of it. That's the idea here. And this is what an abstract data type is. Where in fact we have this idea of something called a list, or we have this idea of something called a board. But the actual implementation of it is not something that we need to know about. So that's the key idea. And in fact, in Java, there's, for example, there's something like, for example, the Java collections. Has anyone come across that before? Yeah, but there's in fact an abstract class called a collection, right? And there are things which you can do with collections. And actually, collection I think is an interface, but it doesn't really matter. It's just more abstract. And so Java has more ways for us to specify that stuff. But we can have a certain level of abstraction in C as well. And we could talk about a sequence. It's harder to do abstraction in C, but good programmers do it. And we'll learn some of the basics of doing it in this course, but it gets a lot more complicated. So we won't delve too deeply. But enough for you to be able to design some simple data structures in a good way. Just something for you to think about is this idea of design patterns. it's used in object-oriented languages a lot. And design patterns are just recipes. They're ways which we have successfully done something in the past. And since we've done it successfully in the past in this way, we can do it in the future. Now, we can use, even though design patterns are an object-oriented thing, mostly, you can use them in C, and this little book here I found is kind of useful to give some examples of that, but we won't really delve into that much more than that. Just give you that book, and if you want to have a look at it, go ahead. Okay. Code style. Have any of you worked on projects with other people and ended up having an argument about this? That will be everybody. Yeah. But typically, that kind of... Well, I think it's probably important to have a convention that everyone on the project agrees with. I mostly code in kind of a GNU style. I think probably the Linux kernel style guide is probably one which I've got a bit of affinity with for obvious reasons, but the thing is about having a consistent approach. So, indentation. How many spaces? Do we use tabs? Placement of braces, same line or next line? Personally, I'm mostly a next line person, but people get kind of rather upset about this thing. So, indentation or not of case labels. One of the text editors I use quite often, Emacs, by default doesn't indent case labels. So that's one thing that I don't like about that. And I changed the style guide that it uses so that it actually does indent case labels. I think that's an important thing. And naming conventions. So do we use camel case, or do we use underscores, or what do we use? Now, I personally prefer underscores, and I'm not really a big fan of camel case, but a lot of you probably are because of you coming from kind of Microsoft based programming languages and all that kind of stuff, and also Java has kind of adopted by and large the Microsoft approach. Whether that's good or not is something people can debate. It's fine. So here are a couple of code standards you might find useful. There's the GNU standard. There's the Linux kernel standard. So I'll very quickly have a look at these. So I might start with the... I'll start with the GNU one. Oh, that's annoying. Let's try that again. Okay, so now I'll open up a new window. And this one, yeah. We're not really going to go through all those slides, but that basically explains the kernel style guide. Yeah, feel free to go through them yourselves at some point. So, magic numbers. What's a magic number? Yeah. In this course, we consider anything other than a 0 or a 1 to be a magic number. So, for example, the 0th element of an array is well known to be the first element. Yeah. Or the +1 for a string, we know that's the null terminator. But I would actually hash define, I would hash define something like, for example, extra chars for the two characters at the end with fgetS. Okay. 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 So we would avoid them using hash defines, but even better than hash define is the use of an enumeration. Yeah? People remember enumerations from previous discussions? Okay, so what's an enumeration? Yeah, but what's so special about an enumeration compared to other types? Yeah, but it's a sequence of, it's a named sequence. So, um, so avoid magic numbers through use of hash defines. I prefer enumerations if it's actually a series of related values. And the use of well-named variables. Okay, so so what's recursion? Yeah. So, recursion is the idea that we have a function that has a base case and it has a recursive call. Yeah. And using this, we can actually break down a problem into smaller parts. Although, what's the problem? For a language like C, it's not really the best way to do it. Yeah, because we have the runtime costs of a function call. Yes, so we have recursive call, which has another recursive call and so on, and each recursive call involves pushing data onto the stack as parameters and then jumping storing the return address and then jumping to the first line of that other function. And if we're doing that over and over and over again, each one has a cost. Sam, what's a language recursion is good in? Generally what are called functional languages. So Scalar is an example of that, or the F sharp, yeah. SML. There's lots of there's Racket. There's lots of languages where this is where they're optimized for recursion, and in fact recursion is the building block for the language. C is not like that, unfortunately. So recursion could work very well for some problems, not so well for others. So let's have a look at some code. Okay. So now Alrighty, let's have a look at factorial. Okay. So I've got a main function here which all it's doing is calling fact for each number and then prints out for between 0 and max fact. And so fact is in fact the recursive function. So if n is less than or equal to 1, return 1. Otherwise, return n times fact of n minus 1. Okay. So now let's just run that. So that was reasonably quick. Not too many problems. Okay. And it's pretty simple. I would say that in this case the recursive version is a simpler program than the iterative, but it would take longer to run. It's not really obvious with factorial that slowdown in terms of time. So let's have a look at iterfact. So this is the iterative version. It's more complicated, isn't it? Than the recursive version. So recursion can give us some nice code. But it takes longer to run, and I'll prove that to you in just a moment. So let's have a look at Fibonacci. So one of the things is that we use a lot of stack space for recursion. Is that a problem? Because every time we do a recursive call, correct stack space is awfully limited. In fact, I'll just show you. There's a function that I can use in Unix called ulimit, which tells me the limits. And I do ulimit minus a, and we can see here stack size in kilobytes. So there's 8 megs of stack space. You run out of that pretty quickly. So it's not ideal for that reason. Okay, let's have a look at Fibonacci.c and have a look at why this is not such a great idea. Okay. Well, what I'm doing here, and I'm kind of jumping ahead a little bit, is I'm going to time. Now, the time function isn't the most accurate in the world in the sense that it only measures seconds, which is probably not the best approach. There are better functions around, but we're not going to talk about them. So, let's have a look at our implementation. So we have, if number is less than or equal to 0, we return 0. If number is 1, we return 1. Else, return Fibo num minus 1 plus Fibo num minus 2. Why is this a problem? But what's the problem here? Fibo num minus 1 plus Fibo num minus 2. How many recursive calls are there? Right. So for the first 10 Fibonacci numbers, basically I have 2 to the 10 recursive calls. What's 2 to the 10? Yes, 1024. So 1024 recursive calls in order to calculate the 10th Fibonacci number. That's not really ideal, is it? Okay, so let's actually see what you see. It's slowing down as it calculates larger and larger Fibonacci numbers. And now it's got, I think I can. So in order to calculate 45 Fibonacci numbers, it took me 18 seconds. What about iterative? So if count is less than or equal to 1, next equals count, else next equals first plus second. And so it's essentially doing a interesting iterative. Yeah. Now, let's actually run this and see how long it takes. Wow, did you see that? And in fact, I can use the time function, the time command, to actually see how long it took. .03 seconds in total, really. So 3 milliseconds versus 18 seconds. So the message here is, for anything other than really simple problems, recursion is not the right approach in C. In other languages, it's generalized into the right approach always. So in things like functional programming languages. C, no. Avoid recursive solutions unless they are really simple. Yeah, those times might have changed because it's a newer machine and that kind of thing, but the principles are correct. Now here's a really dumb use of recursion. Where is it? Yeah, let's go with recursive random. Okay. Actually, before I do this, just give me a sec. Yeah, let's quickly go through this time stuff and then I'll come back. Time in C is measured in seconds since the 1st of January 1970, which was the beginning of the Unix epoch. It's basically when Unix was invented by Ken Thompson. Okay. Alrighty. So the first function we're going to look at is time, which returns a time t value, number of seconds since the 1st of the 1st, 1970. And if we pass in null here, then it simply returns a number of seconds here but writes nothing here. But if we actually pass in a pointer to a time t, it'll write the value there as well. So let's have a quick look. So it means that we've got two options here. We could pass in a pointer, or perhaps not. Either approach would work. So here one thing I've done here is I've defined a macro, which is basically a shortcut, which defines that I've got this thing called 2 days, which takes in num and then converts that to days. So it divides num by seconds, minutes and hours. So we're actually going to deal with them in a lot more detail later, but I use them because it's just a nice, like, basically it's a string replacement. So it replaces this call to 2 days with the answer. So it happens at compile time rather than at runtime. So it's faster and all that kind of stuff. But we'll actually get to them at a later point. Okay, that's... So days since the beginning of the Unix epoch, 17,154. And I could actually, okay, let's... I'm just doing this for verification. I'm just going to divide that number by 365 to get number of years. 46 years since the beginning of Unix. That seems about right. Since 1970 to 2016, 46 years. Yeah, that's good. Okay. I'm not going to go into these in too much detail. Diff time takes in 2 time t's, which is in fact a type def of a long, and it gives you the difference between them. So I've provided you an example in difftime.c, but I'm not going to go through it. We could even set the time, but you can't do this unless you are the super user on the system, because time has implications for a whole range of things. You can actually fake when a file was modified and lots of other things. So it's a privileged thing. But I'll give you an example there. And there's this struct tm, which can be used for a whole range of time functions. So local time takes in a time t and returns a struct tm pointer. So it's broken down into this kind of thing. We can convert back from a struct tm to a time t using make time. And there's others as well. I'll let you go through them yourself, really. We won't have a lot of focus in the course on time functions, but they're really useful and we need to know about them for random, which you need for your assignment. So there is a random function which returns a value between 0 and rand max, where rand max is the largest signed integer. Now, but before you can actually start using random though, or pseudo-random sequences, you must seed the generator. Give the generator a starting point. Otherwise, you'll get the same numbers over and over and over again. And we don't want that. We don't want the first player to always be white. We want them to be red sometimes. Or the first player in the player array to always be white. We want them to be red sometimes and white other times. And in order to do that, we need to seed the random number generator with srand. And srand takes in an unsigned int. And so the standard way to actually seed the random number generator is a call to time null. So we are getting the seconds since the Unix epoch began. So the good thing about that is that the seed will be different every second. But if you need seeds which are even more different than that, then you can't use this built-in library. You'd actually need to use a third-party library for it. And, you know, that may be what you need. Actually, I'm not a really big fan of this particular library. Now, these have lots of uses. Games is a big one. But let's have a look at, say, random.c. Okay. So we seed the random number generator here. Yeah. And we're modulusing, remember, rand gives us a number between 0 and rand max. So num will hold a number between 0 and 9. Yeah. So this is a guessing game. I'm going to read in each number. And if the number was not numeric, print out an error message. So let's, and it just keeps going until we guess the right number. So let's try this. Try a higher number. Oh, got it in 2 guesses. But and you see the number is different each time. So the important thing is that I seed the random number generator, then I generate the number, and then I do user input stuff, and that's the whole program. It's really quite simple program. Okay. Okay. So one other thing I wanted to actually talk about is in okay, in this case we're using srand, and then I've written a function called random. And this is a particularly dumb implementation of random. So I seed the random number generator, I grab a random number, if it's less than 10 I return it. Why is this stupid? This is really stupid. Why is it really stupid? What's the probability, given that we have a number yeah, very low probability that this will ever succeed. So what will happen then? There is a website named after this phenomenon that I'm sure many of you have visited. Correct. This will generate a Stack Overflow. Remember, we've only got about 8 megs. So it's really... Now that segmentation fault is because of a Stack Overflow. Because I have a really dumb implementation of random. Okay. So that's the material for this week, which has been more a bit of a focus on algorithms and that kind of thing. But hopefully now you've got all of the information you need to complete your assignment.